Good afternoon, everybody. My name is Amelia Hames. I'm here with the Office of Communications, and I would like to welcome you to today's Engage session featuring Hubble and all the amazing things that it's done over the last 35 years. So without further ado, I would like to welcome Dr. Krista Peters-Ladard to kick off today's event.
Hey, good afternoon, folks, and happy Earth Day also. So I'm Krista Peters-Ladard. I'm the Director of Sciences and Exploration here at Goddard Space Flight Center. And I am so happy to welcome you on this happy occasion to celebrate an anniversary of our, one of our most iconic missions, the Hubble Space Telescope. Hubble's lasting impact on astronomy and humankind is evident as we reflect on the impressive 35 years of science observations, which have provided us not only with groundbreaking discoveries, but also beautiful images that drive us to new frontiers in exploration. And amazingly, the telescope is still going strong, not only thanks to our dedicated team at Goddard, but also our critical partners, the European Space Agency, the Space Telescope Science Institute, and Lockheed Martin Space. So if you're one of those team members or partners, raise your hand and let's give them all a hand. Yeah, so thank you for coming, and we have such an exciting program for you today, featuring several of the men and women behind Hubble. But before we begin, we're going to take a few minutes to enjoy some Hubble highlights. So let's roll that video.
We are all explorers. It's in our DNA. We explore the depths of our oceans, our planet's inner regions, and its desolate outposts. We never stop exploring. Galileo opened our eyes to the heavens with his use of a newly invented instrument, the telescope. He started an exploration renaissance of the sky that would take us to the moon and beyond. For over a quarter century, the Hubble Space Telescope has been unlocking the mysteries of the universe, allowing us to explore the edges of space and time. From nebulas to galaxies, from newborn stars to planet formation, from exoplanets to our own planets, and from dark matter to dark energy. Hubble has allowed us to see the breathtaking details of the universe never before seen. We salute the thousands of men and women from around the world and in space that have given humanity this incredible exploration machine. While we celebrate its past and dream of its future discoveries. The Hubble Space Telescope, inspiring the explorer in all of us.
Hello, everyone. Thanks for being here today. I'm Claire Andrioli. I work in the Goddard Office of Communications. I'm going to be moderating today's panel. And here with me, I'll just start left to right, we have Dr. Allison Youngblood, who is the TESS project scientist and also a user of Hubble data. Dr. Nicole Colon is the operations project scientist for the James Webb Space Telescope and was formerly the deputy operations project scientist for Hubble and also a user of Hubble data. And then we have Jim Jeletic, who is the Deputy Operations Manager for the Hubble Space Telescope and also leads our outreach team here at Goddard. And Dr. Jennifer Wiseman is the Senior Project Scientist for the Hubble Space Telescope. So thank you all for being here today. All right, we are going to start off with, I'm going to ask you guys a series of questions to just have a fun conversation. It's going to be trying to touch on 35 years of excitement of the Hubble Space Telescope in about 40 minutes. So we'll see how we do.
1 minute per year, it sounds
yes,
like.
there
Okay,
you
all
go.
right.
I like it. Let's see if we can meet that goal. And then we'll toss to questions from the audience. But first, let's start off with a fun question for the group, which is, what is your favorite Hubble image? Jennifer, do you want to start?
I sure do. So my favorite image is also the favorite image of many, many people around the world, but it is the ultra deep field, and I want to see if our AV crew is magically putting it up. Yes, it is. All right. So the ultra deep field, as I'm sure you all have basked in this image a long time, but to me, I never get tired of looking at this because it is, as you recall, just pointing the Hubble Space Telescope in a direction where there weren't many nearby stars to drown out the image. It's just collecting light for what would be the equivalent of many days. And so the faintest objects show up. So every little smudge in this image is, for the most part, another galaxy outside of our own. And when you think about that, galaxies can contain billions or hundreds of billions of stars. Each one of these little smudges could contain hundreds of billions of stars. And we now know most stars in our own Milky Way have at least one planet, so that is quite likely true for these other galaxies as well. And then, of course, we've been exploring the third dimension in this image for many years, the distances to these galaxies, which are like a time machine, right? So we can now probe this image to see how galaxies have changed and evolved over cosmic time and made our universe more hospitable to life. So that's why I love this image.
Amazing. I love that. This is one of my favorites, too. Yep. How about you, Jim?
All right, so mine is a phenomena. So it's called the V838 Mon light echo. And I like it, first of all, it's a gorgeous image, but also because it's this concept where it looks like this cloud is growing over time, but it's not. It's actually all there, and you're actually watching the time delay it takes for light from a flash that the central star had to reach the outer portions and actually light the whole thing up.
Love that. Nicole?
So I wanted to start first, because I work on Webb, I have to say that some of my favorite images show Hubble and Webb together. And so this is one example of a galaxy. It's actually a series of galaxy images that were released recently, and it's showing Hubble on in the visible and then Webb in the infrared, and kind of meshed together. And it's just really stunning looking at images like this because it really showcases how these observatories can work together to, provide just that more complete picture of everything we're looking at in the universe. And, as an example, with the visible light with Hubble, you see that there's a lot of dust in this galaxy, but the dust absorbs starlight, and you have dark lanes through the galaxy in this spiral face-on system here. But then with Webb in the infrared, the dust actually glows, and those are the bright orange and green. That is the dust itself. So you see different paths are traced when you look in the visible versus the infrared. And so that really just gives us insight into
we can look at different angles and see how stars are forming within these galaxies that are embedded within the dust with Webb. But then Hubble gives us a really nice view of things like the hot ionized gas, thanks to its ultraviolet and visible capabilities. So I love examples like this, but I cheated, I picked 2 images. And so the second image is one of my favorite from Hubble. It's a smiley face. And and I love this one because, well, it's cute, and it was my wallpaper for a while, right? But it's really shows a cool phenomenon in the universe that you have 2 bright galaxies that look like eyes, but then this region in space is actually a massive galaxy cluster, and so it's bending light from distant galaxies and causing these arcs that look like smiles. So it's really bending, magnifying more distant galaxies, and it allows us to study those more distant galaxies thanks to this like gravitational lensing effect. So this phenomenon, when the universe lines up in the right way, where we can see even further into the early universe is amazing, and I just love what this represents. It's you look in space and you're happy.
Amen to that. How about you, Allison?
Yeah, I picked the Mystic Mountain region of. Oh, it's on. Okay, it's on. I picked the Mystic Mountain region of the Carina Nebula. So I wanted to pick a nebula because that's what I studied when I was an astronomer in training, and just with using Hubble data, and just the colors are amazing. But this is, like a 3 light-year long pillar of dense gas. There are stars forming inside, so this cloud of gas is getting eaten apart by stuff in it and also without it. Really massive stars that have already formed elsewhere in the nebula are kind of tearing this cloud apart. And you can see kind of the wisps and certain jets. And there's also a Lord of the Rings connection with this, and I love Lord of the Rings.
Love that. Yeah, this one truly is iconic. So, obviously these are all beautiful images, but they're so much more than that. They represent such amazing science, and, to that point, Hubble has quite literally rewritten the textbooks of modern astronomy. Jennifer, this is a question that I want you to kick us off with. What has Hubble really taught us about the universe? What are some of the most significant discoveries that have come from Hubble data?
And you want us to finish by 2:00, is that okay?
Do the best you can.
Hubble has changed everything about how humanity understands the universe, how we see the universe, how we investigate it, and even the kinds of questions we ask. So I think, you can kind of march either out from the solar system to the widest widths of the cosmos or the other direction, but at every scale, Hubble has made phenomenal discoveries that have changed our understanding and changed the kinds of questions we ask. So I think on the largest scale, we understand much more about the expansion of the universe, right? One of the driving reasons that the Hubble Space Telescope was built and funded was to refine our understanding of the expansion rate of the universe, which was we had error bars like a factor of 2, understanding the expansion rate, and that, of course, feeds into our understanding of the age of the universe. So that was one of the driving motivations for having the Hubble Space Telescope in the first place. Well, that measurement has been refined and refined and refined over the decades with Hubble, to the point where not only do we know the precise expansion rate of the universe right now, but it's causing us problems, right? Because it doesn't actually mesh exactly with what would be predicted from our models from our cosmological models, matching with what we measure from the cosmic microwave background radiation from the very beginning epochs of the universe. So we have what's sometimes called a Hubble tension, because we're the Hubble constant, which really measure or is that expansion rate in our current epoch, doesn't match what should have been predicted. So this is, I think, one of the most phenomenal discoveries from Hubble throughout its mission. And a Nobel Prize was awarded based on Hubble and ground-based telescopes, telling us that not only is the universe expanding, and we're measuring this expansion rate very carefully, as I just described, but that expansion rate, at least for the last few billion years of cosmic history, seems to be accelerating, getting faster This was something that was not taught when I was in graduate school. We knew that the universe must be slowing down in its expansion because that's what matter does, right? It pulls things together. So expansion rate, detection, refinement, and the discovery of dark energy is one of the major contributions of Hubble. As we move back in towards smaller scales, we have learned that individual galaxies are often merging with other galaxies. I think one of the greatest revelations of Hubble in its early years is how common galaxy mergers are, especially in the early universe. So we now know that galaxy mergers are a really important part of the development of galaxies, including our own Milky Way, and that this merging fuels star formation. And so we get these bursts of star formation in these merging galaxies. And then moving in to even a more local scale, Hubble opened up our eyes to the fact that stars are still forming, and they form with dusty disks around them in our current epoch. So when we look at star-forming regions like Orion and others with Hubble, we see these protostars or these young stellar objects, and we often see them encircled by dusty disks. Well, we now know, of course, that these are planet formation zones. Hubble helped us understand and confirm that there are actually supermassive black holes in the cores of galaxies. We didn't know that. It was theorized, it was thought to be possible. Hubble confirmed by looking at the motions of gas in the cores of galaxies that supermassive black holes are common and probably inhabit the cores of every galaxy at some level. So that is a major discovery of Hubble. And then in subsequent years, we've studied that surrounding material falling in, feeding black holes, and the jets that get formed from some of that material falling in and then being ejected because of magnetic field activity around these supermassive black holes. And then, of course, Hubble was one of the first, I think it was perhaps the first observatory to show us how to discover or to characterize exoplanet atmosphere. So in our own galaxy, in our own neighborhood, exoplanets were starting to be discovered in the 1990s, and Hubble contributed by helping us understand how to analyze the atmospheric content from these transiting exoplanetary systems. That technique is now being used not only by Hubble, but also by Webb and many other telescopes, and that has transformed our understanding of the nature of other planetary systems. So those are some of the highlights that come to mind, and I know I probably missed many of your favorite Hubble discoveries out here in the audience, but my point here is that Hubble has contributed to every part of astrophysics, including understanding the interstellar medium and the cosmic web of material that connects galaxies. And of course, our own solar system being very active. Hubble's helped us understand right from the start that our solar system is not stagnant. You know, we saw that comet crashing into Jupiter early on in Hubble's mission, and we've been watching the weather change on the outer planets for many years. We've been actually looking at the moons of other planets as well and understanding their dynamics, even their potential habitability, some of these ice-crusted moons. So I think I'll stop there, but you can see that Hubble contributes to every aspect of astrophysics.
It's seemingly never ending.
Right.
I think the exoplanets in particular, I find fascinating, Hubble's connection to exoplanets, because you think of that as really an area of study that was in its infancy when Hubble launched. I mean, we barely knew that they existed at that point, and now look at all of the contributions that Hubble has made to advance exoplanet research in particular. I mean, you both are exoplanet gals. Do you have anything to add to that? I mean, even recent discoveries that have been made that have really advanced that field in particular.
I'll start. Yeah. It's just to add to what Jennifer said, you know, with Hubble, it really showcased with its near-infrared capabilities that there's water in a lot of exoplanet atmospheres, you know, which was not a surprise, but that's something that we wanted to look for and see, you know, is water common in the universe, right? You know, we need water here on Earth to survive. And so what does that look like in other planets outside of the solar system that don't orbit stars like the sun? And we find out, water is very common, but also clouds are very common, hazes are common, atmospheric dynamics is like everything that we see in solar system planets. Hubble provided evidence of that in exoplanets, so that really kind of set the paradigm for big surveys of exoplanet atmospheres. So it's been just a treasure, trove of data with the Hubble mission, and then with Webb, adding on, there's a lot more that we can learn to complement at different wavelengths. Yeah,
For sure.
Yeah, another thing that Hubble's been contributing to in exoplanets is the study of atmospheric escape from planets. So imagine if you took Neptune and stuck it well inside Mercury's orbit, much, much closer. What would happen? You'd probably have stuff evaporating off of it. And Hubble has seen this with its spectrographs of a planet called GJ436b, where it has this long tail of hydrogen trailing its orbit. And it's estimated that, over the next million to billions of years, that planet will look very different because it's losing so much mass. Yeah.
So fascinating. Go ahead, Jim.
So I want to just mention that if you had told somebody in 1990 that Hubble was going to characterize the atmospheres of exoplanets, they would have said you were crazy. So that's a real kudos to the astronomical community that they figured out how to use Hubble for all kinds of things, especially the characterization of exoplanet atmospheres.
Yeah, for sure. Are there any other, just because this really speaks to the prominent role that Hubble has continued to play as the field of astronomy has evolved over 35 years. Are there any other more recent discoveries of note that you really feel illustrate that point?
Lots of them. All right,
What's your best?
I'll throw out one. So I mentioned that early in Hubble's mission, it confirmed the presence of supermassive black holes in the cores of other galaxies by, you can't see a black hole directly, but you can see the motions of stars and material orbiting that central black hole. And by measuring very precisely the motions and velocities of stars and gas around the core of a galaxy, you can discern the mass of what must be in the middle there. And it was very clear that it must be a compact, very massive object in the cores of other galaxies. More recently, Hubble has been used to discern something called an intermediate mass black hole. So these supermassive black holes can weigh as much as millions or even billions of times the mass of a star, of our sun. Hubble's now detecting black holes that are not necessarily in the middle of galaxies, but are in the middle of clusters of stars, like globular clusters. And by measuring, once again, the motions of stars very carefully, Hubble researchers have discerned that in some of these clusters, it looks like there's an intermediate mass black hole at the core, maybe weighing a few hundred times the mass of a star. So that's really interesting because we knew about these supermassive black holes and we knew about individual stars that die and turn into black holes, but this intermediate class is a new detection from Hubble, and it's really enabled because Hubble's been around enough years that we can monitor the motions of stars over decades, and we can make these kinds of discoveries that we could not do with just a snapshot. So that's one example.
Perfect. So the next question that I was going to ask, someone who's watching online actually beat me to it. So thank you, Tammy. I'm going to go ahead and ask Tammy's question. Can you share how Hubble's UV measurements in particular are still unmatched after 35 years, and also how they're complementing the IR and VIS measurements from other observatories?
Well, I'm going to hand that over to our UV specialist over here, but first let me just say that that's an important point. A lot of people ask me, public ask, well, Hubble has been great, but now we've got other telescopes like Webb. Do we still need Hubble? And the point of our NASA Great Observatories paradigm that we've had for successfully for so many years is that we need multiple wavelength bands to get the full scientific understanding of whatever it is we're trying to do. So Hubble is now being used by scientists mainly to focus on observations in visible light and ultraviolet light. You really need a telescope in space to do those ultraviolet light observations, and that complements what telescopes like Webb do so powerfully in infrared light and Chandra in X-ray light. So I'm going to defer to Allison over here for a discussion of what is super cool about Hubble's ultraviolet capability.
Yeah, Hubble's unmatched in ultraviolet observatory, the most powerful facility ever. And the ultraviolet is just this really rich region. I mean, as astronomers, what we're learning about the universe, we learn through light. There's information encoded in light. We look for different transitions of atoms and molecules, ions, and the UV has the highest density of these tracers. It has the richest availability of it. And so that's why the UV is this really desirable region. And Hubble, yeah, with its unprecedented sensitivity, is still like the best game in town. And you know, some examples of like of coordination that Hubble is doing with Webb, for example. So you know, facilities like Webb are going out and characterizing these planets. I know a lot of you in this room probably work in heliophysics, planetary science, earth science, you know, and I think you all know how important it is that we go out and measure what the sun is doing, because the sun's energy controls so many properties of the atmospheres and surfaces of planets in our solar system. And the same is true for all of these exoplanets that we're finding. We need to know what those host stars' output is, especially in the ultraviolet, because ultraviolet photons, they drive chemistry in the atmosphere. They can control what the chemical makeup is. So when Webb goes out and measures molecules, you need that stellar context that Hubble provides with the ultraviolet in order to interpret that chemistry.
And I mean, that's a really good point, just with respect to other missions that have come online, you know, since Hubble has launched. There's been quite a few missions that have come onto the scene over the past 35 years. Obviously, JWST, which we've already talked about a little bit. Are there any other just examples that anyone wants to touch on of just how Hubble observations are helping to kind of complete that picture that other telescopes are providing us, JWST or otherwise?
Yeah, maybe I'll jump in first because this is a good follow-up to what Allison was just talking about with focusing on Webb and Hubble coordination. There's actually, just last year, you know, to showcase how new and, you know, rapidly evolving these programs are, there's a new Director's Discretionary Time program that was announced to study rocky exoplanets around low-mass stars that are cooler and smaller than the sun, but so they're often more active, and so that this program is actually taking 250 orbits of Hubble time, and then 500 hours of JWST time, and using that to take Hubble, study the stars, understand how the stellar activity and radiation impacts the exoplanets and the evidence for their atmospheres and atmosphere dynamics and all that. So Webb is going to search for the atmospheres, and Hubble will look at the stars and study them in detail, so that together you get that picture of how, you know, likely are these rocky planets to have atmospheres in the first place. And that is, you know, again, a excellent example showcasing how these observatories work together to understand a big open question in the field, because again, these stars are very active, and so the planets we study are also really far away, you know, relatively speaking, and the atmospheres are really tiny signals, so we need that sensitivity from Hubble and Webb together to understand the big picture. So that's, yeah, one example that's really powerful, showing how they work together.
Love that. This is kind of a good transition into the next question that I had, which is more just respect to, you know, the fact that Hubble's been operational for such a long time. There's so many new missions that have come onto the scene. How is Hubble still being used by scientists, particularly maybe earlier career scientists who might be, you know, lured by the newer, shinier things that have come on the scene?
Yeah, I'll take that. So astronomers have been cutting their teeth on Hubble data since Hubble launched. My own career, I started doing little research projects as an undergrad with Hubble. Did that in my graduate career, postdoc, and then now as a professional. And one thing that really has changed in the past 10 years is that, Hubble goes out, astronomers propose for time on Hubble, and they say, I want Hubble to go look at this galaxy because it's going to answer these really high priority questions. Well, less than 10 years ago, policies changed and they implemented dual anonymous peer review. And that really enabled the scientific merit of proposal ideas to be the focus rather than the experience of the team. And this opened the door for so many early career scientists to begin leading their own Hubble proposals. And that career development opportunity as like a young scientist is unparalleled. I think that, if you talk to many scientists, astronomers, I think you'll find that a lot of them had some critical early experience with Hubble data and research that have gotten them to where they are now in their careers.
I love that. That's a great point. I want to switch to the operations side of the house for a second, because obviously, the fact that Hubble has been operational for 35 years, that's no easy task. Jim, how has the Hubble team really pulled this off? And how much longer do you think we can keep going?
Well, first of all, I'd say you have to have a great team, all right? And so we truly have brilliant engineers and scientists, both here at Goddard in the mission operations area and at the Space Telescope Science Institute up in Baltimore, who does all our science operations for us. And that includes a contingent of ESA people who work on the day-to-day types things up there as well. We also have to give thanks to the servicing missions and the astronauts. There's no question that the only reason we're here today is because of them, because we probably wouldn't have lasted 5 years from launch without that first servicing mission. So they truly did a great job, especially the last servicing mission in 2009, which left us in outstanding shape. But what we do today is I'm going to kind of put some into some logical buckets. We take a look at all the hardware on the spacecraft and try to figure out how to make it last longer or work around it. So the first group is just, how can I change the way I do operations to make things last longer? So the best example is our transponders. So, the death of a transponder is how many times you turn it on and off. And so if you can reduce that number of times, you can make it last longer. So what we did was we changed from doing a lot of short transmissions to fewer, longer transmissions, and therefore turning it on and off is less frequent. Then there's another category, and that is what happens when a piece of hardware fails? How are we going to compensate so we can still go on with the mission, still do the great science? And I think the best example of that is we're currently in one gyro mode. So when Hubble was launched, and for years, at least almost 20 years, it was you got to have 3 gyros. There is no way you can stay accurately pointed and have the jitter or the amount of movement you have when you're taking data be as small as it has to be unless you have 3 gyros. So the team proved us wrong. And now we have 1 gyro. We've been operating in 1 gyro since last summer. And before that, we were operating in 1 gyro not to get on target, but once we were on target to stay steady. And we've been doing that for years. So we figure out how to compensate for hardware that's problematic or isn't working. What's our workaround for it? And then the third one is that there's stuff you can do on the ground. So for example, the detector on the advanced camera for surveys has a lot of radiation damage. And so if you took a look at the real images that come down from it, they all have like streaks after all the bright objects. And it almost looks like comets and that. But it's a well-known item. And so scientists at Space Telescope Science Institute said, I think we can compensate for this. And sure enough, in the post-processing of the data, all those streaks can be taken out, and you can get what the real picture is supposed to look like. And so that detector, from a scientific perspective, is almost brand new. So I think by grouping these things and taking a look at how we can work around, how we can make them last longer, or how we can compensate maybe on the ground is how we've gotten to where we are. As far as how long we're going to last, again, space is a harsh environment. You never know. You never know what's going to get us. there could be a collision, and that could get us and be catastrophic to us. But for the most part, we have done detailed analysis with other groups at NASA on mean time to failure of the components of the instruments and the components of the critical hardware. And everything indicates that we should still be able to do groundbreaking science well into the next decade. So hopefully nothing will surprise us again, but you never know.
There's always surprises. But I feel like that, the story of the ingenuity behind Hubble is very much, in my opinion, part of what makes the telescope so iconic and what makes it such an inspirational story to people around the world. Because it started right at the very beginning, right? With, there was an error in the optics that had to be corrected, that everyone had to work to address, and, ultimately ended up yielding these iconic images that we know and love today. And the stories have just continued from there, just everyone working together to keep the telescope, at its peak performance over 35 years, which is just amazing.
Could I add a little something
Please.
to the? I'm just continually impressed, being a scientist, but I am not an engineer, at how this expert team on the ground here manages to address Hubble's technical health and occasional glitches, and even making improvements to Hubble's technical capabilities without being able to put their hands on the telescope, right? So we haven't had hands on Hubble since 2009, and yet this team is able to do incredible technical work on Hubble just through remote commanding and through innovative ideas that generate from the team here. And I think that's one of the major strengths of NASA and of everyone here and at the Space Telescope Science Institute and other places that are working on Hubble. So, this is, I think, a lesson learned from Hubble for other missions as well, that we've learned how to work with a mission that we might not be able to touch with human hands. And of course, the servicing missions have been a huge part of Hubble's success leading up to now. And, future missions may be beyond, if they're at L2 or something, they may be beyond human reach, but not robotic servicing reach. So we are informing robotic servicing plans for the future as well.
So I just want to add one thing to that, and that is that even though I'm an engineer, right, I should not be impressed by this, but I am. The fact that these guys can take a look at just data and figure out, oh, that had to be a higher energy particle hit on this chip. And I'm like, how did you figure that out? And they're right. And so we can flip the bit back or whatever that got flipped and get Hubble back doing science. But they do this all the time without putting their hands on it, like Jennifer said, by looking at just data. And I just find that amazing, because they really have to know the hardware inside and out to do that.
It's like a NASA version of the game of Clue, a little bit. So obviously, yeah, the story of just the commitment and the effort that goes into yielding these iconic images, that's an inspirational story in and of itself. But Jim, what impact do you feel like the Hubble images that we have as a result of all of this effort, what do you think the impact has been around the world that's been felt by people who have seen these images?
Well, for those of us who grew up watching the original Star Trek series, and I can tell you that when I go back and watch it now, granted it's iconic, it's really hard to look at those artist drawings of what the universe looks like and that. For those people who grew up in that time, Hubble left an impact in that now we know what the universe really looks like, and these images are gorgeous. For those that were born, say, in the 1980s, just before we were launched or whatever, 1990 or afterwards, that's the only thing they've known. They know what the universe looks like, and it's gorgeous, and they've been enthralled by it. So I think the images have helped the world become more enamored with astronomy, and that. I think the technology that was developed to help get us to that point has also impacted the world. And so, you see everything from, which impacts your personal lives too. Our detectors are used in mammography equipment now in the fight against breast cancer. When you go to a hardware store and you want to match a paint color, those machines are using filters technology that was developed for Hubble. When you watch a speed skater win a gold medal for America in the Olympics, their skates were polished by Hubble technology. And it just goes on and on. The batteries, and this was a new one that just came out a couple months ago that I didn't know about. The batteries, the nickel hydrogen batteries we have are now on sale and for mass storage, so like renewable energy plants and other utilities and that. And now over 50,000 of them are embedded around the world to save energy, store energy, I mean. So I think that has been incredible, and I think the pop culture side of it too has been a pretty incredible result of Hubble. And I mean, you're still seeing new products today, from clothing that some people are wearing today in the audience that are using the latest Hubble images to, I've turned on Netflix like 2 years ago, and I was like, that's one of our images in a new movie that they had out. It was a Ryan Reynolds movie. And of course, my kids were like, shut up, Dad, I'm watching the movie. But you know, you see this all the time. And the nice thing for Hubble is the interest by the press and the interest by the public hasn't waned. So last year we put out 24 science press releases, and that it generated over 5,200 articles online of those press releases. And if you add up all the people who follow those particular outlets, et cetera, and the number of articles, you'd find out it has tens of billions of potential reads on our science and looks at our images because of that. Our social media is some of the largest in the agency, and our X and Facebook account, every 3 to 4 days, we gain another 1,000 followers. So the interest is still there because of these incredible images that we're doing, because of the science discoveries that we're making, and I think we're going to be able to do this for a while yet.
Love that. And I didn't know about the paint filters. That's amazing. I'm getting ready to paint a room in the next couple of weeks. Thank you, Hubble.
Pink or blue?
That's really wild. All right, so we're about to pivot over to questions from the audience. I want to make sure that we get to that. But before we do, I've got one more question I have to ask. What's next? What is next for Hubble?
Well, on the scientific side, we are really excited because Hubble is, we like to think about Hubble's history, but from the scientific community's perspective, we're looking toward the future. And Hubble's a key player in some of the key scientific priorities that the National Academy of Sciences puts out every 10 years in the decadal survey. So we are looking forward to Hubble and helping in cooperation and complement with other telescopes and missions, addressing some of the premier questions in astronomy, or the top questions, and that includes trying to understand dark energy, trying to understand, as we prepare for the Roman Space Telescope, how we understand the universe as a whole, its history, its future. We're looking at transient events. So time domain astronomy is a really high priority right now, and that's looking at transient events in terms of explosions in the universe, that kind of thing. Hubble can provide a unique wavelength input to understanding what those explosions are doing and what's caused them and what they create, but also long-term time domain events. Because we have over 3 decades of quality data in the Hubble archive, we're getting a lot of new science now, why astronomers proposing new observations with Hubble and combining them with archival observations to learn something we couldn't do with just a one-time observation. For example, we're looking at how one team has looked at how the weather on Neptune, the clouds, come and go in sync with the solar cycle. So now we understand the connection between our 11-year solar cycle and how it impacts the weather on outer planets and perhaps more interestingly, what's going on their moons. That's just one example. So time domain astronomy is a hot topic, transient work, trying to understand cosmology and some of these fundamental questions of physics, understanding the exoplanet atmospheres in complement with Webb and other observatories. Those are the few of the things we're really looking forward to in the coming years with Hubble.
Awesome. And I'm glad that you, just real quick, Jim, mentioned Roman as well as, the next flagship mission that's going to be launching here in very, very short time. We're merely months away potentially, but it's being built right now, just up the street here. So if you're here on Center today visiting, please go and check it out. There's a lot of really exciting stuff that's happening in the clean room right now for Roman, and it's going to be, yielding fantastically large images that will really complement the deeper, more detailed observations that Hubble does, and really tell us a more complete picture together with James Webb as well.
And Roman will find things that we can follow up on with Hubble, and so we're really excited about that.
Jim, you were going to say something.
Well, we had a problem with one of our, next thing for the engineering side is we had a problem where we lost redundancy on our payload computer. So we're working on restoring that. And this is, again, credit to the incredible engineers and scientists we have on the team. So they're going to, it was basically protection circuitry for the power supply. And we figured out how to override that, and also how to use the main computer instead of the payload computer to do a lot of the same functions. And there's a lot of very intricate timing. There's a lot of commanding that has to occur that's never been done before in the spacecraft that we're confident that will work, and that. But we're in the process of doing that, and so hopefully by the end of this year we'll have that in place, and we will have restored redundancy again. On the payload computer side, if we ever need it. So I think that's one of the main things, while we're also, we continue to try to optimize our efficiency under one gyro mode so we can get the most science out that we possibly can.
And then one more thing to add, Jim, because we have something new that we're going to be sharing later this week, right? Did you want to mention that, just as a little teaser?
You mean the images?
Uh-huh.
Oh, okay. Well, she might be better for that, but I will tease you with saying we have a bunch of new images coming out tomorrow, and that even though the anniversary date, official anniversary date is Thursday, but we're going to have several new images that are gorgeous that will come out as a 35th anniversary. Normally we only have one, but this time we're having more than one. And then we have a couple videos too that will explain those images and kind of go over what Hubble's discovered in the last year.
Very exciting. Any questions from the audience? You can come up to one of the mics on either side of the room if you have a question that you want to ask. Please do. Don't be shy.
While you're lining up, I just want to mention that these 3 major observatories that are going to be operating at the same time this decade, Hubble, Webb, and Roman, are extremely powerful and complementary. So Roman will see a much wider field of view than either Hubble or Webb. And Roman will concentrate mostly in infrared and red colors of light. And what's seen with Roman will complement or enable us to do more detailed follow-ups with Webb and Hubble. So these are really complementary observatories in terms of fields of view and wavelengths of light, and they're designed for that complementary purpose. So.
Thank you. Go ahead.
On, can you hear me? Oh, okay, good. Peter Krasinski from the Cosmic Origins Program Office. A question for you, Jennifer, about the image that you spoke of at the beginning, the ultra-deep field. And this has been so impactful for astronomy. But I wonder if you could take us a little bit back to the genesis of that image and talk about it from the point of view of, pointing the NASA's most iconic observatory at a blank part of sky where you don't know if you're going to see anything strikes me as kind of a risk. And it was an extraordinary scientific risk that paid off. But could you speak a little bit to how that came about and what the thinking was and how it was sort of justified at the time?
Sure. So this was a product of a part of the Hubble mission that we call director's discretionary time, where the director of the Space Telescope Science Institute is allotted a certain amount of Hubble time to use as they feel would be most scientifically productive, perhaps for things that wouldn't make it through just the competitive normal process of proposal reviews, and yet would provide some kind of data set that would be useful for years to come. So I think this was Director Williams was doing, he wanted to do this kind of just fishing expedition to see what would happen if you just collect light and look deeply into the universe. I mean, we knew there were galaxies out there, so that's not a huge surprise, but I think there was some controversy at the time. Was this a really good use of hundreds of orbits of Hubble time? Because it's so competitive, you know, shouldn't you look for something that you're a little more sure is going to get a concrete result or a concrete observation or something that's answering some specific question? Why would you waste time just looking? And of course, now we know it's not wasting time, that that by collecting light and for many days, we saw visually what people had calculated or in some sense theorized must be out there, but weren't sure they would show up, which is this plethora of galaxies. So that's some of the background here. And these directors' discretionary programs have proved to be incredibly valuable in subsequent years as well, because they enable a set of data that can be mined by the astronomical community for years to come. That deep field not only showed us that galaxies are plentiful, but they've showed us, as I mentioned, that third dimension, finding the distances to these different points of light is challenging. But by doing that, we can see how galaxies have changed over time, not by following one galaxy as it changes over time, but seeing how the populations of galaxies look at different redshifts at different distances. We've had other directors' discretionary programs, the Ulysses program, where I think Dr. Julia Roman Duval is here somewhere, who led that. Was that a director's discretionary program? Yeah, looking at stars using Hubble's ultraviolet capabilities. So now we have this marvelous collection of spectra of stars in the ultraviolet that can be used for science for many years to come. We have the Frontiers Fields program. Is Dr. Jennifer Lotz here somewhere? Yes. So Dr. Lotz is the current director of the Space Telescope Science Institute. But earlier in her career there, she was leading the analysis of Frontier Fields, which is looking, I don't know if that was a director's discretionary time, was it? Okay. Looking at, was that Dr. Sembach's program? Matt Mountain's program. To look at clusters of galaxies that are gravitational lenses and so forth. So those fields have taught us much as well. So all of that first Hubble Ultra Deep Field, I think, set a precedent for the idea of looking and then creating data sets that can be mined for unexpected science for years to come. Yep. Looks like we have questions on both sides.
Okay.
The Hubble Space Telescope has been in orbit for 35 years, and many of the people in our audience today have never known a world without it. And as you mentioned earlier, that was made possible, in part, by 5 servicing missions in orbit. With NASA's growing fleet of orbiting instruments, what future do you see for servicing missions to help satisfy our scientific community?
Well, I'll start out and just say that, you know, Hubble wouldn't have had the mission that it's had without servicing. The first servicing mission actually enabled us to address a problem in the optics, as you've heard, and dramatically change the future of this mission into something incredibly successful. The subsequent missions have enabled us to keep Hubble upgraded and repaired, and so that it's still as an observatory doing science at the cutting edge. And so now newer observatories are being facilitated to enable servicing. Now, what that looks like, you know, depends on the particular mission, whether, you know, it's astronauts doing EVAs, you know, that was appropriate for a mission in low Earth orbit. Maybe not so easy if we're starting to put telescopes much farther away, but robotic servicing is something we started developing with Hubble as well. And that's something that surely is in the future for future astronomical missions. I think it's critical that we create a path for servicing. We have to design observatories from the very beginning so that they are serviceable, so that they have, whether that servicing is refueling or whether it's exchanging instruments or parts, they have to be modular so we can have that capability. But I think it's critical for future missions to be serviceable. And do you have anything to add to that?
Well, I think, and this one's, I'm a little out of my league on this answer, but Habitable Worlds is definitely looking, I believe, to make it serviceable. And I think that, they've had some workshops on it and that, and I believe, one of the big concepts, one of the concerns is, well, if you're going to make something serviceable, it's going to cost you a lot more money. But there's a lot of people now that believe that might not be true. That, as long as you design it from the get-go for that type of thing, it doesn't really cost you a lot of money, but it gives you a heck of a lot of flexibility to be able to go up and service. So I think there's going to be servicing in the future. How far out, I don't know. You're going to have spacecraft that allow you to do that, with airlocks and possibly robotic arms or things like that, humans, vehicles. But I think it'll happen again.
Thank you both. Yes.
Okay, this is just a comment about the Hubble Deep Field. Being older, I remember the discussion behind that. I mean, this was a big deal. This was a lot of time. Riccardo Giacconi's discretionary time, he used all of it for that. And there was discussions about what's the best way. You don't know what you're going to see when you look deep. And the discussion centered on, should you look in one filter and you use all that time, you can see much further than if you use many filters. And the other side said, well, we could learn a lot if we had many filters. That adds an extra dimension. And fortunately, the multi-filter approach was taken. And we can say thanks to them.
Thank you for that.
Thank you, Sally Heap.
Yeah, hi. If you didn't know, the stalk, which is where the telescope is controlled, is just near here. And I've been in it when school groups go through. And listening to one of them struck me as interesting because what they had was these big projectors, and you see the deep field happened to be up. And the kids thought it was a live image because they figured it's a telescope. You look through a telescope, and as it zooms, you pan across the sky. So, of course, all the people here at the stalk that control the telescope see a live image of Hubble. That's what they think. Of course, you have to explain to them. So my question is, maybe to Jennifer, when you propose an observation, are you the first to see it? Or do other people get to see it? How does that work?
So observations are proposed every year by science teams from around the world, and then they go through a stringent peer review. And for Hubble, it's still only about 1 in 6 that get selected. Once those selected proposals get scheduled, and the scheduling is very complicated, the observations are done, the data are transmitted back to the ground. There's some initial calibration pipelines and things they go through, but typically that data goes directly to the scientist science team that observed it after those initial calibrations. So, I have to ask my institute folks, are they the first person to see the image? I'm not quite sure whether that's the right, but typically the science teams get the initial access to the initial calibrated data. There are some types of data that go public quite immediately after those initial calibrations, and so they don't have this exclusive access period. Now, we do have this wonderful popular app right now on the website for Hubble that's says, what is Hubble looking at right now? So you can at least find out what Hubble is pointed at right now or what it's doing right now, even if you can't get a live image from Hubble right now. But do you want to add to that, Jim?
I just want to say, Ed, don't be giving away all our stock secrets here. I mean, for years we've been able to pull this off, making people think we can actually see in real time, but we can't. I think, and I'm going to look at our Institute colleagues, though, I think that sometimes they do take a look at some of the images just to make sure that the science data came back properly and that, so they kind of do a quick look check. So not all the time the scientist is the very first person to see it, but since that data is embargoed in that for 6 months, typically, other than that, they are.
By the way, there's also a What is Webb looking at right now app too, yes. So you can find out what both Webb and Hubble are looking at right now.
I think we've got just enough time to sneak in one more.
Okay. Thank you. I asked this question of one of the Hubble scientists a good number of years ago. And I said, if you could take Hubble and push him out to the distance that you can see, turn him around and look back at the Earth, could you see evidence of industrialization in the atmosphere? Something that's not normal, because that might indicate life there. What about now? If you were to put it at that distance, could you turn around? Could you see industrialization in the atmosphere of a planet?
Can I take that?
Yeah, I would love my exoplanet experts over here to answer that question.
So, yeah, a few years ago, Hubble did a little experiment where you can't point straight back at the Earth. It's too bright. But we pointed Hubble at the moon during a lunar eclipse. So, the moon turns red during a lunar eclipse because the Earth is blocking some of the sun's light. And that's very similar to a transit, which is how Hubble and Webb are measuring the molecules that are in exoplanet atmospheres. And so by looking at the moon during the eclipse, we were able to measure ozone, which is not evidence of industrialization, but it's a byproduct of oxygen, which is life, produced by life. Yeah.
And Allison led that study, just to be explicit, right?
Yes, I did.
Yes.
Thank you for that. And that's, I think, a wonderful point to end on, because as we reflect on all of the exciting discoveries of the past, we also look with anticipation at all those still to come. So thank you all for joining. Thank you to our speakers.
I just wanted to mention, I don't know if it'll come up on a slide, but we have some wonderful resources. I don't know if you want to talk about them, but at the website nasa.gov/Hubble, there's a wonderful new ebook on Hubble's greatest discoveries. There's some other resources. If you look carefully, you'll find a tab on Hubble's 35th anniversary with some wonderful apps and ebooks and things that you'll enjoy. So, and watch out for the new images coming tomorrow.
Yes. Thanks, everyone.
Thank you. Thank you.